So in this tutorial, I'm going to go through 4 examples in your chapter 3 using Mathematica to calculate and visualize strain and displacement vectors in Continuum, and to also do different calculations. And in this tutorial, I'm going to introduce a few different Mathematica functions as well. So the first problem that I'm going to go through is a problem on page 147 to calculate the deformation gradient given 3 vectors, given the deformed representation of 3 vectors. So the problem goes: a continuum body deforms such that the vectors, the original vectors dx given by this vector, dy given by this vector, and dz given by this vector, deform to the vectors small dx, small dy, and small dz. We need to find the deformation gradient, and we need to state whether this deformation is physically possible or not. As seen in the I went through this example in within the lectures. The deformation is physically possible or not depends on the value of the determinant of the deformation gradient. And to solve this problem, we need to form 9 equations in 9 unknowns, the 9 unknowns being the 9 components of the deformation gradients. Basically, we need to solve the 3 equations that look like this. We have small dx is equal to a matrix F that has 9 components multiplied by the vector dy, and dz is equal to f multiplied by capital DZ, dy is equal to f dot dy. We need to solve each equation is actually 3 equations because the vector has 3 components, so each vector is actually composed of 3 equations. So 3 equations by 3 vectors, these are 9 equations. Those 9 equations should be enough to give me the 9 components of f. So to solve this problem, I need to introduce a few functions in Mathematica. The first function that I will introduce is Subscript. So to define the components of f, for example f12, I can say it's equal to the function Subscript f1 2, shift enter, and this gives me f1, 2. Another function that I will introduce is Flatten. If I have a matrix that's equal to 1, 2, 3, 4, I can form a list of the entries of the matrix by using the function Flatten. Flatten m, shift enter, will give me the rows, but will make one vector of all the different variables within the m. So I'm flattening the matrix m. The other function that I will introduce is the function solve. So let's say I have an equation that says y is equal to or let's say I have a function that says 2 multiplied by x plus 3 equals 0, and I would like to solve this to find x. I use the function solve. I write the equation, and I write I use 2 equal signs, and this is very important. You have to use 2 equal signs when you use the function solve. So solve 2x plus 3 double equals 0. Solve for the variable x, close the bracket, shift enter, and will give you x. Will give you an assignment for x. It will not evaluate x. It will just give you an assignment saying that x is equal to, or could be the value, or could take the value -3 over 2. So I'm going to use those functions that I just introduced to solve this problem. First, I'm going to start by describing, first by clearing all the variables. So I'm starting from scratch, and I'm going to define a matrix F with the components of this components of the matrix, the deformation gradient matrix. So I'm going to introduce FF subscript FFI comma j, where I is from 1 to 3, j from 1 to 3, and notice that I'm using a different variable for the different components, because I cannot define a variable here f and then use it again inside that function. And I'm going to view f in matrix form. Notice that I'm writing everything in one cell. So all these commands are, when I evaluate the cell, I'm just evaluating those two commands. Shift enter, and here's my matrix that has 9 components, and these are the 9 components that I'm looking for. Then I'm going to write my 9 vectors, my 6 vectors. Dx is equal to 1, 0, 0. Dy is equal to 1, 1, 0. Dz is equal to 1, 1, 1. Small dx, the image of capital Dx, is 1, 0, 0. Small dy, the image of capital Dy, is 0, 1, 1. Small dz, the image of capital Dz, is 0, 0, 1. And the list of variables that I'm looking for, I'm going to call it list of variables, is equal to the flattened f So I'm going to press Shift Enter to view what this is. So the list of variables that I'm looking for are the flattened f, f11, f12, f13, and so on. These are the variables that I'm looking for, and I can find these variables by solving the equation. By solving the 3 equations, I'm going to put the equations between curly brackets and then solve for the list of variables. The first equation is d small x is equal to f double equal f dot d capital X. dy is equal, again use double equal f dot dy, and dz is equal f dot dz. Shift Enter, and the program solves the 9 equations and gives me the values for the different components of f. To utilize those components, I need to store those variables a in a variable called a. So now a is a list that tells me f11 can take the value 1, f12 can take the value -12, f13 can take the value of 0, and so on. Now I need to utilize this in the matrix f. So I'm going to say f is equal to f after utilizing those assignments inside the list A. And let's view f in matrix form. Shift Enter. So here is f in matrix form. To know whether this deformation is physically possible or not, I'm using determinant of f. I'll find the determinant of f. The determinant of f is 1. It's positive, it's greater than 0, therefore this deformation is physically possible. So I'm going to quickly go through this problem again. I'm going to start from scratch. First, I define f as a table of ff11, ff12, ff13, and so on. This is made by using the function subscript and the function table. Subscript ff I and j. I takes the value 1 to 3 and j takes the value 1 to 3. Then I view f in matrix form. Then I write my 6 variables. my 6 vectors, and then I take the variables in F that I'm looking to solve for, and I put them in a list. I call it list of variables by flattening the matrix F. Then I solve the equation dx is equal to f dot dx, dy is equal to f dy, dz is equal to f dz. I'm solving this, so these are 3 equations. The 3 equations are between a list, so between a set of curly brackets, and the list of variables is the list of variables inside the matrix F. And after this, I'm going to view A in matrix form. A is going to be a list of assignments. These list of assignments are assigning 1 to the variable ff11, assigning -1 to the variable ff12. To utilize those assignments, I use /dot, and I use that list of assignment, and that list of assignment I'm taking the 1 row inside A. And that's why I'm going to show you A in matrix form, and then I'm going to take the first row, which is a list of assignments, and use it to replace the variables inside F with their numerical values that were obtained from A. Then I'm going to view F in matrix form, and then find the determinant of F. Let me just here print A in matrix form. Shift enter. So A in matrix form has this. It's a row of assignments. So I'm going to take that first entry, or that row, and take all those assignments and use them to replace the variables inside F. So the next problem that I would like to cover is how to compute the strain measures in Mathematica. I'm going to again start from scratch. So I'm going to quit the kernel, and I have the following problem, which you will find in your book, page 175. So in this problem, I'm going to use the table function to define both the infinitesimal and the green strain tensors for the motion described by the following. I have x1 as a function of x1, x2, x3, x2, the small x2, the deformed x2 component is equal to a function of the original components, and the deformed x3 is equal to a function of the deformed components. We need to find the displacement function, the infinitesimal strain tensor, and the green strain tensor, and we would like to find the infinitesimal uniaxial strain along the direction of the vector u, and the uniaxial green strain along the direction of the vector u as well. So first, I'm going to define my original vector as x1, x2, x3. And remember, these x1, x2, and x3 have to have no values. They have to be independent variables. So I'm just use clear command, even though I'm starting from scratch. Clears any assignments that you have for those variables. So this is my capital X. It's the vector of undeformed. Then I'm going to define a matrix F. This matrix is that matrix of deformation. 1.2, 0.2, 0.2, 0.2, 0.2, 1.3, 0.1, 0.9, 0.5, 1, and then x, the new vector, the new deformation, is equal to f dot x, and let's view x in matrix form. Indeed, x is equal to 1.2x1 plus 0.2x2 plus 0.2x3, 0.2x1, plus 1.3x2 plus 0.1x3, and so on. The displacement vector u is equal to the position, or the new position, minus the old position. I can view u in matrix form. You can see u has three components: u1, u2, u3. Given u, I need to find the strain, so I have the infinitesimal strain matrix. Or before we find the strain matrix, we can find the grad u, which is the gradient of u. This matrix is made out of a table of the partial derivatives of ui with respect to xj, where I is between 1 and 3 and j is between 1 and 3. ui is the first u when I is 1 and x1, when I is 1 and j is equal to 1. This is partial derivative of the first component of u, which is u1, with respect to the first component of x, and the first component of x is x1. So partial u1 by partial x1 gives me the first component of the matrix. Partial u1 by partial x2 gives me the second component, and so on. I'm going to view grad u in matrix form. So this is the gradient of u in matrix form. The infinitesimal strain matrix is equal to half multiplied by, since this is a number, I'm able to use the star, grad u plus transpose of grad u. The infinitesimal strain matrix in matrix form looks like this. And E green is equal to half multiplied by the gradient of u plus the transpose of the gradient of u plus the transpose of the gradient of u multiplied by the gradient of u. And remember, since I'm multiplying matrices, I'm using the dot and not the star. The star is only reserved for multiplying real numbers. I'm going to then view E green in matrix form. Now notice that the difference between the infinitesimal strain matrix and the green strain matrix is large, and this is because the deformation is large. And since the deformation is large, the two strain measures deviate from each other. One gives me the engineering strain, and the other one gives me the green strain, which is, one is delta over L, and the green is half L squared minus L naught squared, all divided by L naught squared. So large strains, those measures deviate from each other. And to visualize the strain, I'm going to use some 3D measures just to show you some 3D visualization tools, just to see how this strain is applied, or how this deformation is applied on a cube. So I'm going to define a box with the function cuboid. This function draws a cuboid between the two opposite corners. So I'm going to use the first corner as 0, 0, 0, and the second corner is 1, 1, 1. So I'm a cube of unit length, and graphics 3D can be used to visualize box 1. Shift enter, and this is my first box. I'm going to take the same box and make another box by using a function called geometric transformation. This geometric transformation function, I can put an object and the matrix of deformation, which is given here. And I can view both next to each other just to see. And you can see this large deformation. This is the original box, and this is the box after deformation according to the new position function given by f. And this shows you how big the deformation is. So we found the displacement function and the both tensors. Now we need to find the uniaxial strain along the direction of vector u and the uniaxial green strain along the direction of the vector u. So first we define u. U is equal to the vector 1. So I need a different variable because I've defined u here. So I'm going to define here vector u is equal to 1, or let's just call it v because it's easier. So v is equal to 1, 1, 1. So E engineering along v is equal to the dot product between v and the infinitesimal strain matrix dot v all of this divided by norm v squared, or norm v multiplied by norm v, and the green strain is equal to v dot E green. So this is E engineering along v, this is E green along v, the longitudinal strain along v and the engineering strain along v, equal v dot E green v divided by norm v squared. Shift enter. One is 0.87 and the other is 1.31. So you can see that the two strain measures give really big difference between the two. Predict two different values. One because it gives you a measure of delta over L naught, and the other one gives you a measure of half L squared minus L naught squared divided by L naught squared. The next problem is from page 180, problem number 6, and notice that in your book the plots are shown, I think, 2 pages after the actual problem. So they should appear right after problem 6, but I think the plots appear within problem number 7. So you should notice that when you're reading your textbook. So far, most of our, or all the displacement functions that we, or the position functions that we have shown, are given by a matrix F, or a linear position function, which means x1 and x2 were linear functions of the original coordinates. Now in this problem, problem number 6, this is the first problem where we're going to introduce a non-homogeneous deformation. In your first lecture, we talked about the difference between homogeneous deformation and non-homogeneous deformation. And in this problem, we're going to see an example of non-homogeneous deformation. A non-homogeneous deformation such that the strain is not equal at every point. Every point has its own strain matrix. So the strain matrix can be variable across the whole domain, and so can the position and the position vector and the displacement vector. And we're going to utilize Mathematica to view the distribution of the variables, the displacement variables, and the strain variables on that domain, or on the plate that's being deformed. So we have a plate that's 2 units by 2 units, which has a displacement function having the following form. The horizontal displacement is equal to this, and the vertical displacement is equal to that. First, we need to find the deformed configuration function x is equal to f of x. Then we need to find the expression of the infinitesimal strain tensor as a function of the position x1 and x2. Of course, what we're saying here is that the strain is not going to be the same at every point. Every point will have its own strain tensor. And then the expression of the green strain tensor, and we were going to utilize Mathematica to draw the plots showing the displacement, and it also visualized the plate displacements. Then we're going to use Mathematica to draw the contour plot or the contour plots for the following variables. So first, let's see how we can find the deformed configuration function or the position function x. So I'm going to start from scratch again. And I'm assuming that my position, that this happens in a two-dimensional Euclidean vector space. Everything in the third direction is 0. The displacement in the third direction is 0. The strain in the third direction is 0. So I have the original position vector equal to x1 capital X2. The displacement vector is given by 0.2 x1 and 0.09 x2 multiplied by x1. And the position function x, we know that u is equal to the new position minus the old position, which means that x is equal to the old position plus u. And we can view x in matrix form. Shift enter, and here is the position function. The new coordinate of any point is given by this function. Put x1, for example, equal to, for example, I can assign, so I'm going to use an assignment of x1 to assign a value to it. So I'm going to utilize what Mathematica calls rules to assign values or for x1 and x2, and without actually replacing x1 with that variable. And that's by a rule is a list. So I'm going to call this rule. By using an arrow, assign x1 2, or assign 2 to the variable x1 and assign 2 to the variable x2. And I can view x once the rule is applied to x. And this basically tells me that if I use 2 for x1 and I use 2 for x2, in this case x is equal to 2.4 and 2.36. So this gives me the new position of x once I utilize 2 and 2. I can utilize a different variable or a different value, 1 and 1. Shift enter. When x1 is 1 and x2 is 1, the new position vector of that point is 1.2 and 1.09. Now to find, I don't need those rules, but to find the infinitesimal strain tensor, I need to find the gradient of u first. So grad u, which is equal to a table, the partial derivative of u with respect to xj. Here I takes the value from 1 to 2. Remember, we're just working in a two-dimensional vector space, and j takes the value from 1 to 2. Shift enter. Let's just maybe view it in matrix form. Shift enter. And this is the matrix of gradient of u. Notice that this matrix changes according to the location. If x2 and x1, if we're talking about this corner, then we use x2 and x1, the values of this corner, and I get a certain value for the matrix. So depending on the location within that plate, I get a different matrix because the deformation is non-homogeneous. The infinitesimal strain matrix is equal to half multiplied by the gradient of u plus the transpose of the gradient of u. This is in matrix form, is equal to this. I can use the function full simplify, which can take care of a few of the variables. E green is equal to the gradient of u plus the transpose of the gradient of u plus the transpose of the gradient of u multiplied by the gradient of u. And notice that because I'm multiplying matrices, I'm using the dot. Again, E green in matrix form. And notice how this is non-homogeneous displacement, so the green strain depends on the variable or on the value of the point or the coordinates of the point inside the plane, inside the plate. So the first plot that I would like to draw is the vector plot of the displacement function. The vector plot is simply vector plot of the vector u defined on my plate. My plate x1 goes from 0 to 2 and x2 goes from 0 to 2. These are the dimensions of that plate. Shift enter, and this tells me how each point on that plate is moving. You can see right here that the plate is not deforming that much. A point in this corner is deforming in that area, in that direction. A point in this corner is deforming in this direction. A contour plot will give me a color map showing the intensity of any of the variables on the domain. For example, I can plot the contour plot of u, the first component of u, when x1 is between 0 and 2, x2 between 0 and 2, on my plate. And I would like to show the contour labels. I want to know the numbers. Shift enter. And that tells me that a point here has moved horizontally less than 0.05. A point between this line and this line has moved horizontally less than 0.1, a value between 0.1 and 0.05. A point in this area has moved horizontally more than 0.35. So this gives me a contour of the intensity of the value u1 on the whole domain. I can plot the contour plots of many different variables, of all the other variables, for example, the vertical displacement. This tells me that this whole area has moved vertically less than 0.05. Between those two contours, this whole area has moved vertically less than 0.1 and more than 0.05. This very small corner has moved vertically a value of 0.35. I can use contour plots of the other different variables, so I need to view all those three. So I can, let's view the green strain 1, 1. The first component in the first row and in the first column of the green strain, view it on my plate from 0 to x, from 0 to 2 for x1 and from 0 to 2 in x2. Shift enter, and gives me a contour plot of epsilon 1, 1. So all this area had an epsilon 1, 1 of around 0.222. Between this contour line and this contour line, this area had a 0.223, and so on. Notice that in your assignments you will have plates with different dimensions, which means those limits of your variables will be according to your plate, will change according to the plate. In the last problem that I would like to introduce, the next problem is on page 184, and we've gone through this problem in class as well. We have a strain rosette that measured the strain along that measured the longitudinal strain along 3 directions. These directions are the direction of the vectors A, B, and C, and the strain values were 0.005, 0.002, and negative 0.001. And we need to find the principal strains and the principal directions. So basically we need to find the different components of the strain matrix. So first I'm going to define the strain matrix. I'm going to call it E matrix. I'm going to use the table command and use the function subscript that we defined earlier, and I'm going to call it EM. I'm going to call the components EM with the subscript I and J, and we're using here a two-dimensional because it's a surface. We're assuming it's a two-dimensional vector space, so I goes from 1 to 2 and J goes from 1 to 2. Shift enter, or let's view EMAT in matrix form. Shift enter, EM11, EM12, EM21, EM22. Now we know that the matrix is symmetric, so I could just simply replace EM21 with EM12, or I can just add this as an equation in when I'm trying to solve the different equations. So the first variable is A, so the first vector is A, the second vector is B, and the third vector is C. And I would like to solve the equations that say the following. The first equation, first I'd like to solve for the list of variables that are inside by flattening EMAT. They're inside EMAT, the matrix epsilon, the matrix of strain. Those variables are now in the list called list of variables. So this is what I would like to solve for, list of variables. And I need, the list of variables has 4 unknowns. I'll show you. The list of variables have EM11, EM12, EM21, EM22. So basically I need 4 equations for those 4 unknowns. The first equation is A, the strain along A, which is A dot EMAT dot A, divided by norm A squared, equal 0.05. And another for B, B dot EB divided by norm B squared is given by 0.002. The third equation is C dot EMAT C divided by norm C squared is equal to negative 0.001. And we need a fourth equation because we've defined the matrix using 4 unknowns. And so the fourth equation is saying that the emat to 1 is equal, again use double equal sign, is equal to the, so the off-diagonal components are equal. Emat the component 2, 1 is equal to the component 1, 2. Now these are 4 equations in 4 unknowns. Shift enter, and here are the 4 values for the 4 unknowns. I'm gonna put this, see this is a list of assignments. I'm gonna call this A, or I already used A, so I'm gonna call this sol or solution 1. Solution 1 is a list. I'm going to utilize the first row in that list, which looks like this. I'm going to utilize this and say emat is equal to emat after utilizing this first row of assignments or rules. Shift enter, and here is my matrix. And of course the eigenvalues and the eigenvectors, since it's already diagonal, the eigenvalues are 0.005 and negative 0.001, and the eigenvectors are 1, 0, and 0, 1. Or you can simply write eigensystem of emat, shift enter, and you can view EV in matrix form. First eigenvalue, corresponding eigenvector, second eigenvalue, and corresponding eigenvector.